Okay, we'll continue. Lagrange. So the question says find the point on the sphere x squared, y squared, z squared equals 4 farthest. So that's an indication max. Farthest to point 1 minus 1, 1. So you're maximizing distance. So that's the function you're maximizing. So that's your fx. Distance would be your fx. And the distance is basically x minus the x squared, y minus the y becomes positive, and z minus this squared. And this here was the subject to, which is x squared, y squared, z squared minus 4 equals 0. So again, you find the gradient, the derivative for this, 2x minus 1, y plus 1, z minus 1. You find this same for g, 2x, 2y, 2z, and you apply Lagrange. So for the first one, it would be 2x minus 1 equals 2x lambda. So basically from this one, lambda equals 2x minus 1 over 2x. So 2x minus 2, if you take it inside, over 2x. You can cancel the 2, so x minus 1 over x. X over x is 1, and then 1 over x. This is lambda in terms of x. If you do the same thing for the y, 2y plus 1 equals 2y lambda. Then lambda from here would be 2y plus 2 over 2y, so that's y plus 1 over y, that's 1 plus 1 over y. And if you do this and this, 2z minus 1 equals 2z lambda, then lambda equals 2z minus 2 over 2z. 2z over 2z is 1, and this over this is 1 over z. I'm going to erase some of this to show you what we accomplished so far. So we have lambda equals 1 minus 1 over x and 1 plus 1 over y, 1 minus 1 z. You can make lambda and lambda equal. The 1 and the 1 cancels. Cross multiplication, negative y equals x, or basically y equals negative x. I can set the lambda and lambda here equal 1 minus 1 over x equal 1 minus 1 over z, cancel, cancel. Eventually will give you z over z equals x. So we have y equals negative x and z equals positive x. I can put them all in g. If you put them in g, you have x squared, y squared, z squared, minus 4 or equals 4. So that's x squared, x3, x squared equals 4, x squared 4 over 3. So x is positive, negative, the root of this. Root of 4 is 2, root 3. That means what? We have the point x, if you take the positive, so 2 root 3, y would be negative of x, so minus 2 root 3, and z is x, so that's the first point. There is also another point. If you take the negative of this, y is the negative of this, so it becomes 2 over root 3, and z is this. So we have the 2 points. After finding the 2 points, you plug them back into your f function. And I believe I did this, so if you plug them, the 2 root 3, negative 2 root 3, positive 2 root 3 gives you 7 minus 12 over root 3, and that would be your minimum. And if you plug negative 2 root 3, positive 2 root 3, negative 2 root 3, will give you 7 plus 12 over root 3, and that would be your maximum. Good? Okay. So far we covered 2 ideas, the absolute max, absolute min, and how to do the Lagrange multiplier. There are also integrals. You will see in the exam quick integrals, nothing really special. There will be a question, integral, pretty much straightforward. For example, like I have 0, 1, 1, 2, xy, do the dy, dx. Integrate this with respect to y, xy, y squared over 2, plug 0, 1, and then integrate the result x. You plug 1 for y, so that would be x plus half, and 0 cancels everything. You're going to integrate this. That's 2 over 2, half x. You plug the 2, you plug the 1. 2 gives you 2 plus 1, and 1 gives you half plus half, and 3 minus 1 is 2. So that's pretty much straightforward. I give you another one with the numbers, number 2, also very straightforward, nothing special. Question 3 in quick integrals, sometimes when they ask you the question, you'll see that it's hard to do it in the order given. Like this is for number 3. 0, 1, 1, 2, x, xy to the power 5, dx, dy. If you try to do this dx, it will be almost impossible to do it. Because you'll see that, okay, do we do u substitution? Do we do it in any other trick we know of? You'll see that no. So here you might think that maybe we need to switch. Now, how do you actually switch the endpoints? This is a little bit tricky. Now, one way to switch the points is to say, well, are these equations or numbers? If these are just numbers, switching would be very straightforward. Just switch the order. If they're equations, later on you'll see that if it's equation, you need to do something special. But here, it's only numbers, so you make the switch dy dx. In terms of y, then you say, well, the inside is to the power 1, so all I need to do is add 1 to the exponent, divide by the number, and over the multiplier of yx, so cancel with this. I need to put the 0, 1 for y, and then integrate in terms of x. You put the 1, gives you 1 plus x to the power 6 over 6. Put the 0, gives you 1 to the power 6 over 6. This is what we're integrating from 1 to 2. You integrate this to the power 1, so you just say, add 1 to the exponent, divide by 7, and there's 6, 42, and this is 1 over 6x. And you put 2 and 1. And if you put 2, it gives you 3 to the power 7 over 42, and 2 here gives you 1/3, minus, you put the 2, put the 1, gives you 2 to the power 7, 42, this is half, sorry, and, no, this is third, right? And 1 here gives you 1/6. You can do this in the calculator to find what the final answer is, or just leave it as it is. So, this is the idea of just straightforward, quick integrals, or if you need to switch. And if you need to switch, if it's only numbers, just switch the numbers and you're good. And then you get into more integrals. Where it's actually not just numbers, equations. So for example, we'll do a quick integral with equations. From an equation to an equation, and in x dy dx. So the integral of this is xy. We need to plug this and this. Plug the x, gives you x squared plus x, minus, plug the x minus 1 into y, gives you x squared minus x. We integrate this from 0, 1. You'll see this and this cancels. You have x minus x, so basically you're integrating 2x, which is x squared. You put 1 and 0, 1 minus 0, 1. That's pretty much straightforward. Now, what if it's a little bit more complicated? Again, this is the integral, the quick integrals we did when it was multiple double integrals, but numbers. Here, double integrals, equations. So for example, you have this one here, root y to 1, 0 to 1, and it's 1 plus x squared to the power 9 dx dy. You'll see, you look at it, if you do the dx first, integrating this with respect to x, almost impossible. Because x squared, I need to have the derivative outside to be able to do it u sub. I need to have an x outside. I don't have an x outside, so we need to switch. But it's not as easy as the one we did, where it's only numbers. No. This one we need to switch, and it's equations. Okay, this is how you do it when it's a double integral. For triple integral, it's a little bit more complicated. Here you have x equals 1, x equals, this is the upper curve, and x equals root y is the lower curve. X equals 1, this is x equals 1. x equals root y, which is also y equals x squared, would be this curve here, where this point is obviously also 1. Now, if you want to switch this, if you do that rectangle like this point belongs to root y or x squared. And this point here belongs to the 0. So if I make the dy first, I know that I need to go from 0 to x squared. And the numbers for dx, or the x numbers, starts from 0, finish at 1, so 0, 1. So you integrate. With respect to y, it becomes y, you plug x squared and 0. Let me just look at the question. Oh, the inside was 3 here. Sorry. Then whatever you get, you're integrating from 0 to 1. Put x squared, it would be 1 x squared minus 0 dx. Now, this integral is done u sub. But really, Fendon doesn't do it u sub. He does it by what's called guessing. You don't need to do it u sub if you can guess. Now watch and listen carefully. If you notice that the inside has a derivative outside, so the derivative of x3 involves x squared. So all you need to do, when you see a function inside, derivative outside, just take this, add 1 to the exponent, divide by the number. So when you see a function here, and there is a 3 extra from the derivative, so times 3. So when you see a function inside and the derivative outside, hide the derivative, add 1, divide by the number, and there is a 3 extra from the derivative, so also divide by 3. And you put 0 and 1. 1 gives you 2 to the power 10 over 30. Put 0, 1 to the power 10. 1 to anything is 1 over 30. So this is the answer. Okay, so we'll do the next one, where it's also hard and we need to switch. So the question is, integrate root x over 3 and 1. This is e y cubed dy dx. You'll notice that if you actually need to integrate this with respect to y first, it will be almost impossible. So switch. To actually switch, the upper is 1, so your upper is y equals 1. And the lower is y equals root x, or root x over 3. So to sketch this, you'll notice that if you plug 0, will be 0, and if you plug 3, it will give you 1. So it looks like it's going to go like this, but it's like a curve. I need to make the switch, so if I make the switch like this, now this point belongs to the curve y equals x over 3, which is y squared x over 3, meaning x equals 3y squared. And this point is 0. So, if I make the switch, my upper would be 3y squared, my lower is 0, and it's ey cubed. Now I can put the dx and then the dy. Now, in the y, I go from 0 to 1. So if I integrate this dx, it would be constant x, and we put the two limits, and integrate the result from 0 to 1. Put this, would be this times 3y squared minus 0. Now we integrate this. Now you'll see, this is the function, this is the derivative. So when it's e to a function, and the derivative, the integral would be just the e. So when it's e, it's like, when you do e, integrate x squared to x, as ex squared. When you see a function and times its derivative, e raised to a function times derivative, the integral would be the e. So e to a function times derivative, it's only the e. And you put 0 on 1, e to the 1, e to the 0, so the answer e minus 1. So this is the answer, and that's the end of part 2. When we come back, we'll keep doing the integral, but now we get into, so we did the integrals numbers, easy. We did the equations, we did one straightforward equation, and we did one involving switching. We're also going to do a couple where you need to make the switch to polar. We'll see this in part 3.